In this video, we're going to go over potential energy and how we can calculate potential energy of a system. So with potential energy, that is going to involve changes in intramolecular bonding. So as a reminder, intramolecular bonding, that's going to be your covalent bonds, so bonds between two non-metallic elements, or ionic bonds, which are between a metal and a non-metal. Okay, so breaking and forming new bonds between atoms is what's going to be changes in intramolecular bonding, and that only comes about when you have a chemical reaction going on. All right, so when we're calculating potential energy changes, we're calculating enthalpy. So enthalpy is sometimes referred to as heat, and the symbol for that is delta H. So it's a measure of the total energy possessed by a substance. Enthalpy is a property of a system that reflects its capacity to exchange energy, which is usually heat in this course, and it's why we use the symbol H as in for heat, but sometimes you can calculate other forms such as light or electricity. Okay, with the surroundings at constant pressure during a physical or chemical change. So enthalpy can be different for a substance depending on its state. So you can have a different enthalpy value for when a certain substance is in a gas state versus a liquid state versus its solid state. And it'll be at different temperatures. So the substance will possess greater kinetic energy at a greater temperature. Now, the thing about enthalpy is we can't measure the enthalpy of a system. However, we can measure the change of said enthalpy of a system. Now, usually we measure the change of enthalpy of a system by looking at temperature changes as energy is given off or absorbed. Okay. Actually, one thing before we keep on moving on, let's make sure we highlight this because that's pretty important because it comes into play later on. All right, so communicating enthalpy. So you should know that when you're dealing with an exothermic process or an exothermic reaction, delta H, or change in enthalpy, is going to be negative. So as a reminder, an exothermic process is when heat exits your system, okay, or energy exits your system. So since energy is exiting for an exothermic process, that's why change in enthalpy is going to be negative because you're losing energy. Okay, so the energy is lost by a system to its surrounding, energy is given off, and the products are going to have less energy than the reactants. So this is going to become important, especially once we get to potential energy diagrams. Meanwhile, endothermic processes, change in enthalpy is going to be positive. So as a reminder, endo sounds like enter. Energy is entering the system. So since energy is entering the system, you could think of it as your system is gaining energy, which makes sense why your change in enthalpy is going to be positive if it gains energy. Okay, so energy is going to be absorbed, and if you're looking at a potential energy diagram, which we will get to later, the products are going to have more energy than the reactants. Now, when we talk about change in enthalpy, we also have to talk about the change in molar enthalpy. Now, often, molar enthalpy is going to have a subscript to help us figure out what type of reaction is happening. Okay, so you should be able to read these subscripts and know that they're talking about different types of reactions and the molar enthalpy involved in it. So if we have this little F subscript, that's the molar enthalpy of formation. So whenever you need to have your molar enthalpy of formation values, where you can find this is on page 4 and 5 of your data booklet. So starting off on page 4, you can see it says standard molar enthalpies of formation. So all of these are molar enthalpy of formation, and they are all in the units of kilojoules per mole. So you're going to have to know this. Now with the next one here, it's the molar enthalpy of decomposition. So the D stands for decomposition as that little subscript there. And how you can figure it out, since decomposition is the opposite process of formation, how you can figure it out is you can take the molar enthalpy of formation of whatever substance the question's asking about, and if you times it by -1, you get the molar enthalpy of decomposition value. Okay, so heads up on that. The delta CH, that's the molar enthalpy of combustion, and then if it's just trying to be general, then delta reaction H, that's molar enthalpy of reaction there. Okay, so just so you know, these little circles here, all they stand for are standard conditions. So your reaction is taking place at 25 degrees Celsius and 100 kilopascal. Now, do you need to know 25 degrees Celsius and 100 kilopascal? The pressure, not really. And for temperature, usually temperature is given to you in the question there. So I wouldn't worry about that too much. All right, so molar enthalpy can be measured in kilojoules per mole. Sometimes it's joules per mole, but usually kilojoules per mole. Enthalpy is either measured in joules or kilojoules. So a substance will have more enthalpy if it takes part in a physical or chemical change. So for example, if you have a small firecracker of TNT, that's going to have less enthalpy because there's less mass than a large stick of dynamite. So therefore, we try to standardize our enthalpy measurements so that they can be easily compared. That's where molar enthalpy comes in. So molar enthalpy, which is usually measured in kilojoules per mole, allows us to see which substances release more or less energy, that should say. More or less energy during a change because they all involve the same amount. So by amount, we mean moles. Okay. So when we're talking about systems and their physical or chemical changes, kind of just dependent on what's happening in that system, we're going to be interested in like how much energy is being lost or absorbed. So if we look at one substance with a certain amount of energy and it's being converted into another kind of substance with a different amount of energy, we can figure out the change in enthalpy or the molar change in enthalpy. It kind of just depends on what your question's asking for. But like in this example here, right, we have methane being burned in the presence of oxygen. It gives us carbon dioxide and water vapor as well as energy. Okay, so when your energy term, if you're looking at a chemical equation, if your energy term is on the product side, that's your dead giveaway that you have an exothermic reaction. Okay, and since you have an exothermic reaction, we can expect our molar enthalpy to be negative, as well as our change in enthalpy to also be negative. Okay, that is something that's going to come up later. Like if you have a negative molar enthalpy or change in enthalpy, you should know that that is talking about an exothermic reaction. Okay, if your energy term in a chemical equation is on the product side, you should know that that is an exothermic reaction. Okay, moving on to our formula that we're going to be using when calculating enthalpy. We're going to be using this. Potential energy is equal to moles times the molar enthalpy of a reaction. So this is not in your formula sheet, or sorry, in your data booklet. So you need to memorize this. Okay, so potential energy can also be represented by change in enthalpy. So change in enthalpy is equal to moles times the molar enthalpy of reaction. So just be aware of this. Potential energy is equal to change in enthalpy. So that's why we can say that these are the same reaction, or sorry, the same equation. Now with moles, to find moles if you're given mass, that's going to be mass divided by molar mass. Mass is in grams, molar mass is in grams per mole. So that's another formula that you're going to have to know in order to use this equation if your question gives you mass of a substance. Now, let's say, for example, the question gave us everything we needed to know for this question, or sorry, this equation. So potential energy is equal to moles times molar enthalpy, but they wanted us to find moles so that we could find mass. Okay, how you find mass from moles? Mass is equal to moles times by molar mass. So you should know all of these equations here. All right, so let's look at our variables. Potential energy, or change in enthalpy, that's measured typically in kilojoules. Moles is in moles, and molar enthalpy is usually in kilojoules per mole. And just like I said on the previous page, this little circle just means that you're using standard conditions, which is 25 degrees Celsius and 101.3 kilopascals. I believe on the previous page I said 100 kilopascals, that's my bad. 101.3 kilopascals. All right, so example 1. The molar enthalpy of combustion of methanol is negative 726 kilojoules per mole. What is the enthalpy change of combustion for methanol if 5 grams of methanol is burned? All right, so let's do our list of givens. So since it asks us what is the enthalpy change, we're looking for delta H. So we got no clue. But we're told that the molar enthalpy of combustion is negative 726. So molar enthalpy of C for combustion, negative 726 kilojoules per mole. And then our mass, that was 5 grams. Okay, so that's 5 grams of methanol. All right, so as a side note here, we know that we're going to have to find moles. The reason being is because if we look at this equation, so delta H is equal to moles times molar enthalpy of some reaction, in this case it's combustion. We're looking for change in enthalpy. We need to do some work to find moles, but we can figure it out, and we already have molar enthalpy. Okay, so first things first, we need to figure out our moles. We've been given mass, so we need to use this equation, because if you have the identity of the substance, you have molar mass. Now, as a quick review, how do we find molar mass? So you might want to do this on an extra piece of paper. I'm going to write this out, but then I'm going to have to erase it because I don't have enough space to do all of this. All right, so methanol, if you've already done the organic chemistry section of this course, this is pretty easy. Methanol, if I did the line diagram, is going to be like this. So we have carbon, and there's 1, 2, 3 implied hydrogens there, and then OH. So that would be our chemical formula for methanol. But if we look at our data booklet here, these are all arranged alphabetically, and methanol is right here. So you can get the chemical formula from here. All right, so how you calculate molar mass is you want to figure out, break it down by how many or what elements you have, and then how many atoms of each element you have, and then the molar mass of each of those elements, and then we're going to do a totals column. Okay, so we have carbon, we have hydrogen, we have oxygen. All right, so carbon, how many atoms of carbon? We have 1. How many atoms of hydrogen? We have 3 plus 1, so we have 4. And we have 1 oxygen. Now, for the molar masses of each of these, we got to look at our periodic table. Okay, so carbon, that's going to be a molar mass of 12.01. So remember, molar mass of each element is in the top right hand corner. For oxygen, it's 16. So let's write those down. And for hydrogen, that's going to be 1.01. So what you're going to do is you're going to take how many atoms you have and multiply it by the molar mass to get your total from that particular element in this substance. So 12.01, 4.04, and 16. And then you're going to add those up. So that's going to give us 32.05 grams per mole. Okay, so again, you might want to write this table out on a separate piece of paper just because there's not a whole lot of room in this question. But this table is how you figure out molar mass for any substance. So make sure that you know this. So molar mass, 32.05. All right. So in this case, first thing we're going to do is we're going to find moles. Okay. The reason why we're going to find moles is because we don't know what change in enthalpy is. So that's what we need to find. So we need to have moles and molar enthalpy before we get going on this. So moles is going to be equal to mass divided by molar mass. So start out with my formula, and then I'm going to plug in my numbers. So 5 grams divided by 32.05 grams per mole. So the grams cancels out. And if I go 5 divided by 32.05, we get that. Okay, so let's write out the first 4 digits after the decimal. 0.1560. Keeps on going on forever. Moles. Okay, Okay, so keep in mind, yeah, I'm writing ... but I'm going to be using the raw number in my calculator. The reason why I only write the first 4 digits is, and not all of them, is because I don't have the time to write all of them. All right, let's go on to part 2 of this calculation. So keep in mind this R is just a placeholder until like what type of reaction that you're doing is actually mentioned. So because it's a combustion reaction, I can switch that R out for a C for combustion. All right, so we calculated that we had 0.1560, goes on forever, moles. And for our molar enthalpy, that was negative 726 kilojoules per mole. So moles is in the top and the bottom, they cancel out. So let's times these together. So I'm taking that raw number, timesing it by negative 726, and we get 113.2605. And the number keeps on going on forever. And that's in kilojoules because that's the only units that didn't cancel out. All right. So before we claim that we're done, let's just check for sig digs. So this number has 3 sig digs, and same with this number. Remember that trailing zeros do count for sig digs. So we got to put our answer in 3 sig digs. So our cutoff line is right on the decimal. So that means we don't need to use scientific notation if the cutoff line is right on the decimal. So negative 113 kilojoules. That's going to be our final answer. Okay, so what does this mean? Negative 113 kilojoules means that when 5 grams of methanol is burned, this reaction is releasing 113 kilojoules of energy. So it is important that you understand like what exactly the numbers that you are calculating mean. So when I say released, that's the word version of the negative. So released in the combustion of 5 grams of methanol. All right, example number 2. What mass of ethanol is formed if 800 kilojoules of energy is released? Okay, so released, that's an important word. Released means that it's going to be negative. So mass, that's what we're looking for. Change in enthalpy. So since it said 800 kilojoules of energy is released, this is telling us that's change in enthalpy. And it's negative 800 kilojoules. Okay, now looking at our formula here, change in enthalpy, that's at negative 800. Moles, we weren't told what the moles was, so we have no clue about that. Okay, but with the molar enthalpy, let's just look at this question. So here's another key word. Ethanol is being formed. So we would want the molar enthalpy of formation. And guess what? We can get that information from our data booklet, page 4 and 5. So moles, no clue. Molar enthalpy of formation. Let's look that up. Okay, so let's find ethanol. So here we go. This is where it is. Okay, so the molar enthalpy of formation of ethanol, because remember that's what all of these are, and the units are kilojoules per mole, is going to be negative 277.6. Okay, so let's just write a little note here. Page 4, data booklet. That's where we got it from. Do you need to write that on a test? Nope, but this is for your notes. This is to help you when you're looking it over for studying. All right. So let's take a look at our formula. Delta H is equal to moles times molar enthalpy of formation. So we have no clue how many moles that we have here. So that's going to be what we want to isolate for in step 1 of this calculation. Step 2, we're going to figure out what the mass is. So molar enthalpy of formation is multiplying moles, so I need to do the opposite, which is divide. What I do to one side, I have to do to the other. That cancels out. Delta H divided by molar enthalpy is equal to moles. So that's what we're going to start off with. So moles is equal to negative 800 kilojoules divided by, that was negative 277.6 kilojoules per mole. So notice how we have same energy units, so those cancel out nicely. All right. So negative 800 divided by negative 277.6. There we go. Ooh. So 2.8818 keeps on going on forever. So dot, 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 and this is moles. All right. So step 2, now that we have moles, now we need to figure out mass. So step 2 is going to be this whole mass is equal to moles times molar mass. Okay. Now, if you think about it for a second, we don't have the molar mass of ethanol just yet, but since we have the identity of our substance, we can figure that out. Okay, so with ethanol, you can look that up. Here's the chemical formula for it. So C2H5OH. Okay, so we're going to use the same kind of process that we did before, so you may want to write this out on a separate piece of paper because I'm going to probably have to erase this because I don't have enough room here. So we're breaking this up with the elements, atoms, molar mass of each atom, and then a totals column. Okay, so what was that? C2H5OH. Alright, so we got carbon, hydrogen, and oxygen. We have 2 carbons. We have 5 plus 1 hydrogens, 6 hydrogens, and 1 oxygen. So oxygen has a molar mass of 16, carbon is 12.01, hydrogen is 1.01. Okay, so we're just going to multiply these out. So that's going to be 24.02. That's going to be 6.06, and then 16. We add these all up, and that's going to give us 46.08. And that's going to be grams per mole. Okay, so that's the molar mass of ethanol. So let's use this number of moles that we just got. Moles, I'm going to have to scooch this over here. Times by 46.08 grams per mole. And now we can just multiply the two. Okay, so we get 132.7953, keeps on going on forever. And with our units, moles is on the top and the bottom, so they cancel out. So our units are grams. So let's look at our question. We're only given one number. So with the enthalpy of formation, since that's a constant, you do not use constants for your significant digits. How can you tell if something's a constant? Effectively, if you got it out of your data booklet, it is a constant. Okay, so 800 kilojoules or negative 800 kilojoules, that is 3 sigdigs. So our answer, our final answer, needs to be in 3 sigdigs. So our cutoff line is right on the decimal point. So we don't need to use scientific notation. And since the number after the cutoff line is higher, 5 or higher, we round up that number in front of the cutoff line. So we got 133 grams. Okay, and this is 133 grams of ethanol. Maybe I should put that in. There we go. Okay. Last example here. What is the enthalpy change when 200 grams of sodium chloride is formed? Okay, so let's do our list of givens. Enthalpy change, that's what the question's asking for. It says 200 grams for our mass. Okay, and then it says that sodium chloride is formed. So I know from here I'm going to need molar enthalpy of formation, and we can find that out from our data booklet. So I'm gonna put it down here. Molar enthalpy of formation. So that was of sodium chloride. So let's look that up. Sodium chloride. There we go. Okay, so that's negative 411.2. And that's kilojoules per mole. So again, how do I know what the units are? You just look at the top of the page and it tells you there. Okay, so reason why I left a little space here is just so I could figure out molar mass. Okay, so with sodium chloride, it's NaCl. Okay, so we only have one atom, both of sodium and of chloride. So if I look at my periodic table, what we're going to be doing is we're going to be taking 22.99 and then adding it with chlorines or chlorides because it's an ion here. So 35.45. So that's going to give us 58.44. So molar mass 58.44 grams per mole. Alrighty, so if we're figuring out change in enthalpy, we already have molar enthalpy of formation, we need to do some work to figure out moles first so we can start using this equation. We can't use an equation if we have two unknowns. Okay, so how we're going to figure out moles is we take mass, divide it by molar mass. So 200 grams divided by 58.44 grams per mole. So let's see what that's going to give us. 200 divided by 58.44 is going to give us 3.4223 goes on forever. Okay, and grams was on the top and the bottom. They cancel out. We're left with moles. Okay, so that's step 1. Step 2, figure out enthalpy change. So let's write out our formula. Now let's plug in our numbers. So 3.4223 goes on forever, moles. So remember, I'm using the raw number I have in my calculator to complete this calculation. And then molar enthalpy of formation, -411.2. And that's kilojoules per mole. Okay, so let's multiply this. -411.2. Okay, so that gives us -1407.2553 goes on forever. So notice how moles is in the top and the bottom, they cancel out. So our units are kilojoules. All right, so looks like the only number we were given was this 200 grams. That has 3 sig digs. So if I count from the far left, 1, 2, 3, there's my cutoff line. So because it comes in front of the decimal, yep, I'm gonna need scientific notation. Okay, so remember with scientific notation, you only want one digit that's not 0 to the left of the decimal. So 1, 2, 3. So it's going to be 1.4, and then, so for this 0, you got to look after the cutoff line. Since 7 is higher than 5, so again, you're looking for any digit 5 or higher is going to round up the digit in front of the cutoff line. Okay, and then we're going to go times by 10. We moved the decimal over 3 spots. Now our original number, don't forget about that negative, by the way. Our original number is bigger than, I should have said, if your original number is bigger than 1 or -1, okay? So our exponent is going to be positive. So we got -1.41 times 10 to the power of 3 kilojoules. And that is it.